So we continue our discussion of Clifford algebras and spinors. Today I'd like to tell you about how the Lorentz algebra acts on spinors, how the rotation group and boosts and so forth act on spinors. And this is part of our preparatory work to being able to discuss supersymmetry. So let's get started. This is Clifford meets Lorentz. So the first statement is that our representation of the Clifford algebra from last time, we called it zeta, and then there was this S vector, which was a series of plus and minus a halves, which labeled the states in the representation, that this representation is also a representation of the Lorentz algebra. Now to see that, we're going to rely very much on this exercise we did way back in the first week of the class, where we saw that the Lorentz generators could be written in terms of these gamma matrices. They could be written as a quadratic expression in these gammas. The Lorentz generators, mu nu, I could write that as minus I over 4, and then a commutator of the gamma matrices, as opposed to an anti-commutator that we've been dealing with up to this point. So we have these generators, and then to describe the representation, it's often useful to have a set of eigenvalues of some of these generators, a maximally set of commuting generators, eigenvalues of those generators to describe the representation. This is just like we do with the rotation algebra back in quantum mechanics, where we have the rotational group and we describe the representation in terms of the Jz angular momentum quantum number. So here, let's look at the M2A, 2A plus 1 generators. I claim that these all commute, and because they all commute, they can be simultaneously diagonalized. And each one of them is like the Jz from quantum mechanics. So you can think of Jz as the angular momentum associated with turning something in the xy plane. Here we have a bunch of these parallel planes. Remember, we're in an even dimensional space, so we can pair up all the dimensions, and we can consider the independent rotations in each of those planes. And the eigenvalues associated with each of those generators, they're going to label our representation. So how does that work? Let's define SA, the spin operator, if you will, to be a factor of I, to keep all these numbers real. This is only going to show up in the time direction. So that's a Kronecker delta that only shows up for the time-like direction. Having a time-like direction is always a bit of a pain here. We always need to do a little bit of adjustment to get the time to work with the other spatial coordinates. And then we have 2A plus 1 for this generator. And I claim that the eigenvalues of this operator are going to be plus or minus a half for each of these rotations in each of these planes. And how do we see that? Well, we can rewrite this, it turns out, as gamma A plus, gamma A minus, minus a half. So we'll prove this in a minute. So have some patience and we'll show you where this comes from. But let's just think about the consequences first. So we have this first object, this gamma A plus, gamma A minus. This is just like the A dagger A operator in the harmonic oscillator. It's just like the number operator in the harmonic oscillator, which tells you which excited state you're in. So here it tells you whether your state is occupied or not. So it's going to have eigenvalue 0 or 1, depending on whether you act with that raising operator or not. And therefore the S operator itself, the capital S operator, will have eigenvalue plus or minus a half. So the whole thing then, with the minus a half, this has eigenvalues plus or minus a half. And these are the little sa, the lowercase sa from before, that labeled our states. So in other words, we've written down an operator now whose eigenvalues we can use to determine what state we're looking at. Okay, so I said I'd prove this in a minute. Let's try and prove it. So let's copy this onto the next page so we see what the target is and get started with that. So here's our operator. So here's our operator, and let's just look at one, and I'll let you do the rest yourself. So let's look at IMO1, which is S0. So if we write that out, that's supposed to be gamma 0 plus, gamma 0 minus, minus a half. It's supposed to be this, but is it? Okay, so let's see what that is. Let's plug in for gamma 0 plus. That's 1/2 gamma 0 plus gamma 1. Let's plug in for gamma 0 minus. That's 1/2 minus gamma 0 plus gamma 1, and then minus a half. And we'll expand that out. So we get a quarter. We get gamma 0 with a minus sign. We get minus gamma 1 gamma 0. We get plus gamma 0 gamma 1 plus gamma 1 gamma 1 minus a half. So gamma 0 squares to minus 1. Gamma 1 squares to 1. And so we're left here with a quarter, 2 plus the commutator of gamma 0 and gamma 1 minus a half. And now we see that these constant factors cancel. And this is 1/4 commutator gamma 0, gamma 1. And by definition, if we just look on the previous page, remember on the previous page we had this is the definition of the generators. This is that exercise we worked out in the first week. So there it is again. And so we see that we can just, if we move this I over to the other side, we get a minus I, and we can check that agrees with the definition of the Lorentz generator. So there we've checked one component, and I'll let you check the others yourself, but you get the idea, I hope. So we have these operators SA, which tell us the spins of the states. Okay, now there's this curious thing that this representation, we've got all these 2 to the d minus 2 states that are determined by all these different choices of spin plus or minus a half. This is not an irreducible representation of Lorentz in the even dimensions we're working in. And how do we see that? Well, as I was saying before, this mu nu, this generator, is quadratic in the gamma matrices. And so if we think about the gammas, instead of gammas as combinations of raising and lowering operators, it's also quadratic in the gamma A plus and gamma A minus. And so it will always flip an even number of spins. I mean, it may be that one of these states goes to several after acting with mu nu, but if you look at how the spins change, everything in the resulting action of the generator on the original state will have an even number of spins flipped. And because of that, you can never change the parity of the number of downspins. The parity of the number of downspins is preserved. So there are going to be states with odd numbers of downspins, and there'll be states with even number of downspins, and they're not mixed through the action of the Lorentz generators. And those two sets of states, they show you how to reduce the original Dirac representation of the Clifford algebra into these two sub-representations. There's a way to make this a little bit more precise. There's a gamma matrix to help perform the decomposition. And it's the following matrix. I take a funny factor of I that means that the whole matrix will have real eigenvalues. And what that factor of I is will depend a bit on the dimension. But then I take a product of all of the other gamma matrices, gamma 0 through gamma d minus 1. This is often called gamma 5 because people are often concerned with four-dimensional representations or representations in 4 dimensions of space-time rather, where you have these 4 gamma matrices, gamma 0, gamma 1, gamma 2, gamma 3, and this is the 5th one that you construct by multiplying the others together. Okay, now to see how this gamma matrix helps us perform this decomposition into these two sub-representations, I want to rewrite this gamma 5 matrix in a different way. So I have a claim that will now show that gamma, I can also write it as 2 to the k plus 1 power times these spin operators that I introduced a few minutes ago. Now how do I see that? Well, I just replace those spin generators with their definition in terms of the Lorentz generators. So I've got 2 to the k plus 1. I've got a factor of I from the time component. I've got a minus I over 4 to the k plus 1 for all the other Lorentz generators. And then I have a product of these commutators, gamma 0, gamma 1, gamma 2, gamma 3, all the way up to gamma 2k plus 1. Now because these gamma matrices anti-commute, I can rewrite those commutators as twice the first term in the commutator. So I can rewrite that guy as 2 gamma 0, gamma 1. I can rewrite this as 2 gamma 2, gamma 3. And I can rewrite the last term as 2 gamma 2k plus 1. So now if you put all the pieces together, you see how I have all of the gamma matrices multiplied together. You can also see how the powers of 2 are going to cancel out. I've got 2 to the k plus 1 in the numerator. I've got 4 to the k plus 1 in the denominator, but then I have 2 to the k plus 1 in the numerator for multiplying all these commutators together as well. I can cancel this I against the minus I to the plus 1 there. And the remaining minus I can think of as I to the minus 1. And so I can write this whole thing as I to the minus k, gamma 0, gamma 1, all the way up to gamma 2k plus 1, which proves the claim since the total dimension is still 2k plus 2. Right. But now with this in hand, with this result in hand, we can think about what it means for the decomposition of the representations. So if we think about the original representation, these zetas with these spins, this list of spins plus or minus a half, this has eigenvalue, this is eigenvalue minus 1 for an odd number of minus a half spins, and it has eigenvalue plus 1 for an even number of minus a half spins. And so we say that the subset of these states with eigenvalue plus 1 form a subrepresentation, a so-called Weyl representation of the Lorentz algebra. And there's another subset of the zeta s's with eigenvalue minus 1 that form a second inequivalent Weyl representation. So we can use this gamma 5 matrix to break our even-dimensional Dirac representations down into two Weyl representations, two smaller representations, each with half the total number of elements. There's a second key feature of this gamma 5 matrix. You can use it, so far we've only been talking about even-dimensional spacetime. But now that we have this gamma 5 matrix, we can use it as the dth gamma matrix in odd dimensions. That it has the appropriate anti-commutation relations with the other gamma matrices to be that last gamma matrix. So in particular, you see that gamma squared is equal to 1, because all the eigenvalues are plus or minus 1, so if I square it, then the matrix must square to 1. And we can also see that it anti-commutes with the other gammas just by writing it out. So the definition here was I to the minus k, product of all the gammas, and then we add it in the other order. And now we see if we try to move this gamma mu matrix to the front, well, what will happen is it will anti-commute through all of the gamma matrices except itself, which it will meet once. And so I'm writing this here, I'm using slightly confusing notation. So, you know, when I wrote D here, I was thinking of D as odd, whereas when I write it here, I'm back in the old setup where I'm thinking of D as even. Okay? And so I'm anti-commuting gamma mu through an odd number of other gamma matrices, all the gamma matrices except itself through which it does commute. So when I push gamma mu to the front here, the claim is that I'm going to get a minus 1. And so I can write this as minus gamma mu, I to the minus k, gamma 0, gamma 1 to the gamma d minus 1, plus gamma mu, I to the minus k, gamma 0, gamma 1, gamma d minus 1, and so the sum is 0. So I'm sorry if that sounded a little confusing. It shouldn't be, and if you pause the video now and you think about what I said, just count in your head whether it's odd or even, keep track of the parity, it should become clear. And if it's not, ask and we'll try to make it clear. But it should be straightforward. I'll just make one last remark in closing, that we could also use minus gamma as the dth gamma matrix in odd dimensions. And this is actually a second inequivalent representation in odd dimensions. If you think about it for a while, you should be able to convince yourself you can't change the sign just of gamma through one of these unitary relations by sending gamma to u, gamma, u inverse. You can't design a unitary matrix that will just slip the sign of gamma and keep all the other gamma matrices the same. Okay, so there's some valuable lessons here about representations of the Clifford algebra. So I think maybe we should just recap here at the end before we bring things to a close. We learned that representations of Clifford are also representations of Lorentz. And we learned about the gamma matrix, the gamma 5 matrix. And it showed us how to decompose the Dirac representation in even dimensions into Weyl, two Weyl representations. And it also showed us how to construct representations in odd dimensions. And these are all really important lessons that I hope you take to heart and absorb as we go on. So the next lecture, we will talk about Majorana spinners, which is a way of putting a reality condition on these representations of the Clifford algebra.